Section: Introduction. In this section, we discuss the advancements in reasoning-focused large language models, LLMs, like OpenAI, DeepSeek R1, and KIMI 1.5, which have improved our ability to tackle complex logical tasks in mathematics and programming. Unlike traditional methods that depend on human-created annotations, the progress is largely due to large-scale reinforcement learning with verifiable rewards, RLVR. This approach begins with a pre-trained model and enhances it through reinforcement learning using simple, automatically calculated rewards based on whether the model's outputs match correct solutions or pass coding tests. This method is appealing because it allows for scalability without needing human input. We believe that RLVR helps models develop advanced reasoning skills, such as enumeration and self-reflection, which are not found in base models. However, we question whether RLVR truly provides new reasoning abilities to LLMs and what these models learn during RLVR training. To answer this, we need to assess the reasoning capabilities of both base and RL-trained models. Traditional metrics often underestimate a model's potential by only considering single attempts at solving problems. To address this, we use the pass at K metric, where a problem is deemed solved if any of the multiple attempts is correct. We explore whether giving the base model many attempts can match the performance of RLVR-trained models. Through extensive experiments across various benchmarks, we compare the performance of base models with RL-trained ones using the pass at K metric. We uncover some surprising results that challenge existing beliefs about reasoning models and RLVR training. First, RLVR-trained models perform worse than base models when the number of attempts is large. While RL-trained models usually outperform base models with fewer attempts, we find that base models can generate correct answers to problems previously thought solvable only by RL-trained models when given enough tries. This suggests that RL training may not enhance, but rather limit, the reasoning capabilities of LLMs. Additionally, we find that while RLVR improves sampling efficiency, it reduces the overall scope of reasoning capacity. Our perplexity analysis indicates that the reasoning paths produced by RLVR-trained models are already present in the base model's outputs, suggesting that these reasoning patterns are not entirely new to the base models. Although RLVR training biases the model towards successful reasoning paths, it also restricts exploration, leading to a narrower range of solvable problems. We also observe that different RL algorithms yield similar results, indicating that current RL methods are not yet optimal. While RL enhances sampling efficiency, distillation can genuinely expand a model's knowledge and reasoning capabilities. Our findings suggest that RLVR, in its current state, does not sufficiently push the boundaries of reasoning abilities beyond what base models can achieve. Overall, our work challenges previous understandings of RLVR and its impact on reasoning models, indicating that RLVR alone may not be enough to advance reasoning capabilities. Section Summary. In this section, we explore the limitations of reinforcement learning with verifiable rewards, RLVR, in enhancing the reasoning capabilities of large language models, LLMs. Our findings reveal that RLVR-trained models often perform worse than base models when given extensive sampling, suggesting that RLVR may not improve and could even reduce the scope of reasoning abilities compared to base models. Section: Preliminaries. In this section, we introduce the basics of reinforcement learning with verifiable rewards, RLVR, and explain the pass at one metric used to assess reasoning boundaries. Verifiable rewards involve a large language model, LLM, that generates a sequence of tokens based on a natural language prompt. A deterministic verifier gives a binary reward, indicating success only if the model's final answer is completely correct, such as matching a numeric result or passing all unit tests in code. We can also add a format reward to encourage the model to clearly separate its reasoning from the final answer. The aim of RL is to develop a policy that maximizes the expected reward based on the distribution of prompts. For RLVR algorithms, we use proximal policy optimization, PPO, which employs a clipped surrogate to maximize the objective. This involves estimating the advantage using a value network. We also include a KL divergence term to prevent the model from straying too far from its original policy. To save on memory and computation, we have seen critic-free variants like GRPO, which estimate the advantage using normalized rewards from a group of responses, and RLOO, which uses a leave one out baseline within each batch. PPO and its variants are part of the policy gradient methods in reinforcement learning, learning from on-policy samples generated by the current LLM. In the context of verifiable binary rewards, our training goal is to maximize the likelihood of correct answers while minimizing that of incorrect ones. We apply zero-RL training directly to the base model without any supervised fine-tuning on long reasoning data. For math tasks, we adopt this zero-RL approach using open-source base models. However, for coding and visual reasoning tasks, we typically start with instruction-tuned models due to training challenges. Measuring the reasoning ability boundary of LLMs is complex, as methods like single-pass decoding reflect average performance rather than the model's maximum capability. For instance, using an average approach, if we sample responses for a difficult problem and none are correct, we get a score of 0. Yet, with more trials, the model might eventually solve the problem, showing that the reasoning boundary can be surpassed. To accurately assess reasoning boundaries, we extend the pass at K metric to all tasks with verifiable rewards. For a given problem, we sample outputs from the model, and the pass at one value is 1 if at least one sample passes verification. Otherwise, it is 0. The average pass at one value across the dataset indicates the proportion of problems that model can solve in one trial, providing a solid evaluation of its reasoning capacity. To reduce variance in computing pass at 1, we follow an unbiased estimation method. For each problem in the evaluation dataset, we generate multiple samples and count the correct ones. This allows us to estimate pass at 1 with low variance. In coding tasks, where we use a compiler and unit tests as verifiers, the pass at 1 value accurately reflects the model's problem-solving ability. However, in math, the risk of hacking increases with more samples, as a model might generate incorrect reasoning but still arrive at the right answer by chance. To counter this, we filter out easily hackable problems and manually verify the correctness of reasoning for some outputs. By combining these strategies, we rigorously evaluate the limits of the LLM's reasoning capacity. Section Summary. In this section, we introduce the fundamentals of reinforcement learning with verifiable rewards, RLVR, and explain the pass at 1 metric used to evaluate reasoning boundaries, emphasizing its role in accurately measuring the reasoning capacity of language models through rigorous sampling and verification methods. We also discuss the challenges of training and evaluating models in various tasks, particularly in coding and mathematics, while addressing potential issues like hacking in problem solving. Section: RLVR's effect on reasoning capacity boundary. In this section, we evaluate the reasoning capacity boundaries of both the base and RLVR models through a series of experiments. Our analysis focuses on 3 key areas: mathematics, code generation, and visual reasoning, with the experimental setup summarized in a table. For our sampling procedures, we set a temperature of 0.6 and a TOP40 value of 0.95, allowing for a maximum generation of 16,384 tokens. We also explore the impact of different temperature settings. Typically, when evaluating the base model, we would include few-shot examples to guide the output and reasoning. However, to maintain a fair comparison, we intentionally avoid using few-shot prompts for the base models, which helps eliminate any biases that could arise from in-context examples. Instead, we use the same zero-shot prompt for both the base and RLVR models, ensuring consistency. Interestingly, while base models often produce unformatted or nonsensical responses without guidance, we find that with enough sampling, they can still generate correctly formatted outputs and solve complex problems. For mathematical reasoning, models must generate a reasoning process along with the final answer. We test various large language model families, mainly QWEN 2.5 and Llama-3.1-8b, using RLVR trained models from simple RL-Zoo. These models are trained on specific datasets with a focus on correctness, excluding format-based rewards. We compare the performance of base and RL models across different benchmarks, including GSM-8K and MATH-500. Our findings reveal that RL-trained models tend to perform better at lower accuracy levels, indicating that RLVR increases the likelihood of generating correct responses. However, as accuracy increases, base models catch up and even surpass RL-trained models, suggesting that the base model has a broader coverage of solvable problems. For instance, on the Minerva benchmark, the base model outperformed the RL-trained model by about 9% at a specific accuracy level. We also analyze the chain of thought, COT, reasoning from the base model, which often produces lengthy and reflective responses, showcasing its reasoning capabilities. While evaluating mathematical problems, we note that correctness is usually judged solely on the final answer, but we emphasize the importance of valid intermediate reasoning. We manually inspect the COTs leading to correct answers on challenging problems, finding that both the base and RL-trained models primarily rely on valid reasoning paths rather than luck. To ensure our analysis is robust, we implement a filtering mechanism to remove easily guessable problems. After filtering, we prompt the models to answer the remaining questions using COT reasoning and inspect the COTs for correctness. Our results indicate that even for the hardest questions, the base model effectively samples valid reasoning paths to arrive at solutions. Section Summary. In this section, we evaluate the reasoning capacities of base and RLVR models across mathematics, code generation, and visual reasoning tasks, ensuring a fair comparison by using consistent zero-shot prompts. Our findings indicate that while RLVR enhances the likelihood of correct responses at lower difficulty levels, it limits the overall problem coverage, with base models ultimately outperforming RL-trained models on more challenging tasks. Section: RLVR for code generation. In this section, we evaluate the RLVR approach for code generation using the open-source code R1 model. We focus on the RLVR trained model, Coder 10 Quen 2.5-7b, which was trained on 12,000 LeetCode and Taco samples over 832 steps, utilizing the Quen 2.5-7b Instruct-1M framework. The compiler provides a binary correctness reward based on specific test cases. For our evaluation, we assess models on Live Code Bench v5, which includes 880 problems from May 2023 to January 2025, as well as on Human Eval Plus and MBPP Plus. Since it is nearly impossible to pass all unit tests by guessing, we use the pass at 1 metric to measure a model's reasoning capabilities. The results show that RLVR positively impacts code generation benchmarks, similar to trends seen in mathematical benchmarks. For example, the original model has a pass at 1 score of 23.8%, while the RLVR trained model scores 28.1%. However, when we sample 128 times, the original model solves about 50% of coding problems, compared to 42.8% for the RLVR model. We also notice that the original model's performance curve remains steep, indicating that its pass at 1 score will likely continue to improve with larger sample sizes, while the RLVR model's curve flattens out. This suggests that RLVR enhances single-sample performance but limits overall problem coverage compared to the original model. In visual reasoning, we focus on models that interpret both visual and textual inputs to tackle complex problems. We use the Easy R1 framework to train QWEN 2.5 VL7B on a dataset called Geometry 3K and evaluate its performance on filtered MathVista Test Mini and MathVision Test Mini datasets. Since both datasets contain multiple choice questions that can be easily guessed, we exclude these from our evaluation, leaving us with 460 problems from MathVista and 114 from MathVision. The effects of RLVR in visual reasoning align with those in coding and math benchmarks, indicating that the original model has a wider range of solvable questions, even in multimodal tasks. To ensure that the increase in coverage isn't due to random guessing, we manually review challenging problems with low accuracy. We find that both the original and RL models have valid reasoning paths for most of these problems, suggesting that the increase in coverage stems from valid reasoning rather than luck. We then analyze why RLVR improves sample efficiency but reduces the reasoning boundary. Our experiments reveal that the base model has a broader coverage of solvable problems than the RLVR trained model. We compare the solvable questions of both models and find that the RL trained model's problems are nearly a subset of those solvable by the base model. To further investigate, we use perplexity as a metric to assess the likelihood of responses generated by the models. We sample problems and generate responses from both the base and RL trained models, as well as from OpenAI's model. The perplexity results indicate that the responses from RL trained models closely resemble those from the base model, suggesting that the reasoning paths utilized by the RL model already exist in the base model. From our findings, we conclude that RLVR does not introduce new reasoning abilities beyond those of the base model. The trends in pass-at-1 scores and perplexity distributions show that the reasoning coverage of the RL model is confined to that of the base model. While RLVR improves sampling efficiency by favoring high-reward responses, it also narrows the reasoning boundary, leading to decreased coverage at larger sample sizes. This reduction in output entropy limits exploration, which we attribute to the nature of RL training. Section Summary. In this section, we evaluate the RLVR trained model coder 10quen2.5-7b on various coding and visual reasoning benchmarks, finding that while RLVR improves single-sample performance, it narrows the reasoning boundary and does not introduce new reasoning capabilities beyond those of the base model. Our analysis indicates that the RL-trained model's coverage of solvable problems is largely a subset of the base models, suggesting that RL training enhances sampling efficiency but limits exploration. Section. Distillation expands the reasoning boundary. In this section, we explore how distillation can enhance the reasoning capabilities of smaller models. We find that distilling from a strong reasoning model, like DeepSeek R1, is effective. This process is similar to fine-tuning a model to follow instructions, but instead of using short instruction response pairs, we use detailed reasoning traces from DeepSeek R1. Given the limitations of reinforcement learning in expanding reasoning skills, we investigate whether distillation behaves similarly. We focus on a specific model, DeepSeek R1 distill Quen 7b, which distills DeepSeek R1 into QWEN 2.5 Math 7b. We compare this distilled model with the base model QWEN 2.5 Math 7b and its reinforcement learning trained version, QWEN 2.5 Math 7b OT0, as well as QWEN 2.5 Math 7b Instruct as a baseline. Our results show that the performance of the distilled model is consistently better than that of the base model, indicating that distillation allows the model to learn new reasoning patterns from a more capable teacher model, thus surpassing the reasoning limits of the base model. Next, we discuss the impact of different reinforcement learning algorithms. We note that the main benefit of reinforcement learning is to improve sampling efficiency rather than to enhance reasoning capacity. We introduce the sampling efficiency gap, which measures the difference in performance between the RL-trained model and the base model. A lower gap indicates better efficiency. To evaluate this, we re-implement several popular RL algorithms using the VRL framework for a fair comparison. We analyze their performance on a dataset called Omni Math Rule, which we split into training and testing sets. Our findings reveal that while different RL algorithms show slight variations in performance, these differences are not significant. The sampling efficiency gap remains high across all algorithms, suggesting that current methods are not yet optimal, and new approaches may be needed. We also make several observations. DAPO achieves higher scores but requires more samples during training. RLOO and Reinforce++ perform well across the board while maintaining efficient training costs. In contrast, Remax shows lower performance, likely due to its unstable training updates. Finally, we examine the effects of training steps on model performance. We observe that while performance improves with more training, the benefits diminish after a certain point. Specifically, after 450 training steps, we see only marginal improvements in test performance, indicating potential overfitting. Additionally, as training steps increase, the model's ability to explore decreases, leading to lower performance in some metrics. Section Summary. In this section, we explore how distillation from a powerful reasoning model, DeepSeek R1, enhances the reasoning capabilities of smaller models like QWEN 2.5 Math 7b, demonstrating that distillation introduces new reasoning patterns beyond the base model's limitations. We also analyze the effects of various reinforcement learning (RL) algorithms on sampling efficiency, revealing that while they improve efficiency, they do not significantly expand reasoning capacity, indicating a need for novel approaches to achieve optimal performance. Section Discussion. In this section, we identify key limitations of reinforcement learning with value regression (RLVR) in improving the reasoning abilities of large language models (LLMs). We explore factors that may explain why RLVR is still limited by the reasoning capacity of the base model. First, we note the significant differences between traditional reinforcement learning (RL) and RLVR for LLMs. Traditional RL, like AlphaGo 0 and the DQN series, can enhance performance in environments such as Go and Atari games without a clear upper limit. However, the action space in language models is much larger than that of these games. Traditional RL methods were not designed to handle such a vast action space, making it challenging to effectively explore rewards if we start training from scratch. In contrast, RLVR for LLMs begins with a pre-trained base model that provides useful prior knowledge, which helps the LLM generate reasonable responses and simplifies the exploration process, allowing the policy to receive positive feedback. Next, we discuss how priors can be a double-edged sword in this extensive action space. Since the responses are influenced by the pre-trained prior, the policy may find it difficult to explore new reasoning patterns beyond what the prior offers. In this complex space, most responses generated during training are limited by the base model's prior. Any response that strays from this prior is likely to be invalid or nonsensical, resulting in negative rewards. As we mentioned earlier, policy gradient algorithms aim to maximize the likelihood of responses that align with the prior and receive positive rewards, while minimizing those that do not. Consequently, the trained policy tends to produce responses already present in the prior, limiting its reasoning capabilities. We believe that training RL models from a distilled model could provide a temporary solution, as distillation can introduce a better prior. Looking ahead, we see potential in exploration methods that can go beyond the prior's limitations in this vast action space to develop more powerful reasoning models. Additionally, we suggest exploring alternative approaches beyond pure RLVR to address these challenges and enhance the model's reasoning abilities.